Hello. Today we'll be proving theorem 2.2.7 out of the book, which states that the limit of a sequence, when it exists, must be unique. And this solution comes courtesy to Professor Headland. So to start off with the proof, let's, as we often do, let epsilon be greater than 0, and further suppose and assume that a sub n goes to A, as well as A sub n converges to B. And these are just our assumptions from the problem. And let's suppose that A is not equal to B. And this is to set up a contradiction later, because for this to be true, we need to have A sub n converging to a value, and converging to two values that would only happen if they're the same for it to be unique. Otherwise, we'd have two limits. And so we're going to suppose that these aren't equal, and we'll show this to be a contradiction. So suppose A is not equal to B, and without loss of generality, let's suppose further that A is less than B. And since A and B are arbitrary constants, we can just have A be the smaller of the two, which would imply B minus A is greater than 0. Now, since A sub n converges to A, and B minus A over 2 is greater than 0, and this follows pretty clearly from this statement here, because you're just dividing by 2. Since both of these are met, we know that there exists some capital N sub 1 in the natural numbers such that the absolute value of A sub n minus A is less than B minus A over 2 for all n greater than or equal to capital N sub 1, right? And put another way, that is, we know our A sub n's are contained in the interval, the open interval A minus B minus A over 2 and A plus B minus A over 2. And so yeah, we know that every term in the sequence is going to be within this average B minus A over 2. It's going to be within that range from our A. And by similar reason, similarly, since A sub n also goes to B, we know that there exists n sub 2 in n, such that the absolute value of A sub n minus B is less than B minus A over 2 again, for all n greater than or equal to capital N 2. I realize I wrote this wrong. This should be n greater than or equal to n sub 1. Oh, sorry for the confusion. And which this is also to say we know A sub n is in this range as well. B plus. And I'm sort of condensing this into one line here just because of space. I don't want to run out of room. And so we know that, well, let's let capital N be the max of our two n's. So, you know, a sub n is going to be in this interval. Well, let's call this I1. And we know it's in this interval, and let's call this one I2. So a sub n is going to be within I sub 1 and I sub 2. However, because of the way these are defined, these are intervals centered around a and b that go out b minus a over 2 from each one. And since this is the average distance between them, this is half the distance rather, it's half the distance between the two, we can show fairly trivially that I sub 1 intersect I sub 2 is empty. And this is a contradiction because we need, following the logic of our assumption, we know that a sub n has to be in both of these open intervals. But since they're completely disjoint, there's no intersection between the two, then it cannot be both intervals. Ergo, our supposition that a is not equal to b is false. Therefore, a must be equal to b. And what does this mean? We've shown if we have a sequence that converges to some value a and some value b, this only is true if a equals b, which means the limit of a sequence, when it exists, is unique. And that's a good place to stop.